Right, hello. So I'm going to try something a bit challenging and see if we can talk through an experiment, a fluoroscopy experiment, and do some simulation. So what we've got here is a paper called by Chang et al. In 2018, and it's called Dose Reduction for fluoroscopically guided injections, and they do a phantom simulation and then they do some patient procedures. And it's quite an interesting paper. It's published in Skeletal Radiography, and they're looking at joint injections in the hip. And what they've done or investigated is what they call dose minimization technique. And dose minimization technique for them involves making quite a few changes. So they've tried to optimize this examination. And the things that they've done is that they've reduced the pulse rate of the machine from 15 pulses per second to about 7.5. They've reduced the field of view, so they've collimated. They've collimated right in, and they used to use a mag. They used to use a mag feature, which allowed them to magnify the screen from about 23 centimeters down to 11 centimeters, and so they're not using that anymore because we know that if we increase the magnification, as we've seen in this picture here, if we increase the magnification, then the dose rate goes up. So from 23 to 11, you can see the dose rates going up quite significantly. So, so they've decided to squint, but you can use a digital. You can actually use a digital zoom to zoom the image up, or you can pull the screen closer, of course. So they're choosing not to use the mag system, and they're lowering the image detector so that it's closer to the patient. So the detector here, what they were doing in the standard, apparently, is they were leaving that with a big gap between the patient lying on the table here and the detector. In fact, we can see the images that they've got here. So as you can see, they were leaving a really big gap between the image intensifier and the patient, and in the experimental condition, they're going to be bringing that gap down. So what we call, that's technically we would call that reducing the object image distance. So, so 4 things: reducing the pulse rate. We know that should reduce radiation dose, right? So instead of having 15 pulses, they're only having 7.5 pulses per second. Coning down from 23 centimeters to 11 centimeters squared. Using the lower mag, which should definitely reduce the dose rate. Because when you reduce the area irradiated of the intensifier or the thing, it tends to increase the amount of dose per frame that the system wants, and using a lower object image distance, because that would be a shorter source image distance as well. Because they kept the distance from the X-ray tube to the patient the same in both cases. So they were just lengthening effectively the source image distance, but the wrong side. Lengthening the source image distance when it's a gap between the tube and the patient being increased is usually a good thing for dose, but lengthening the source image distance where the patient to source is staying the same and the detector's getting further away is usually not a good thing for patient dose. Not unless you're removing a grid as well to leave an air gap instead of a grid. Well, they're not doing that. They're leaving the grid in, I think, in this case. So 4 things at once. Now, you can criticise papers for doing too much because it becomes quite complicated and it's very difficult to understand which of the 4 changes is the most significant. So that's the only criticism, that this paper has got 4 changes going on at once. They also, minimizing fluoroscopy usage too, they also did a bit of training Yeah, so the training also had a dose reduction for the patients, but we're not going to be able to do anything about that. So my plan is, I've got the actual manual here for the machine that they were using. So that's good, we can look at that. I've created a spreadsheet where I've looked at the paper in detail. I've read the methodology, and what I've done is I've created, from what they've described in their methodology, I've created a table here which has got the independent variables. So these are the things that they changed. Yep. I've put the constants that remained the same, the things that they stated remained the same, and the dependent variables, which are the things that they recorded and discussed in their results. Now, like all of these papers, there's a few things that you need to be aware of in terms of some of the things that they mention. They don't actually tell us what the values were, and I've looked in the manual, and the company do not tell you what the values would be either. They just say they have broad statements. So so I have had to make a couple of things up. So as you can see here, in the radiation parameters here in the manual, it tells you the pulse width in milliseconds, that you can change it. So you can change this. Now, I don't know what the pulse width was. I know the pulse rate, they tell us the pulse rate, but I don't know what the pulse width was. And it doesn't tell us in the manual what the pulse width was. All I do know, and it doesn't tell us what the difference in in dose rate would be between the mag and the non-mag. And on page, if I go to page 300 and, what does it say? Page 377 of this manual. They always leave the best stuff at the end. Page 377 of the manual is where it tells us how to set the system up for different doses and dose rates and things. And in here you can see there's quite a lot of detail, but it doesn't really tell you anything significant. I mean, I'm sure if you had one of these machines in front of you, you could work it out what the default settings were by going into the programs and seeing what the default settings were, but it doesn't tell you the settings. So I've had to make some things up that I thought were reasonable in here. So for example, here it tells me the dose per frame was 2.4 microgray per pulse. 2.4 microgray per pulse is the dose that it's sort of like treating as the system dose that it wants. And what it will do is it will alter the pulse width depending on the patient thickness to get that dose rate, I'm guessing. So we don't know what the pulse width was, because that's the way that these things work. You have a set MA and you have a set KV, and then it will fiddle with the pulse width to get the amount of dose that it wants on the receptor to get the image quality it wants without graininess, depending on the thickness of the patient. So I've made up some figures. So, so we do know that the standard condition was 15 frames per second. We do know that the standard collimation, they say 28 centimetres by 28 centimetres. We do know that that works out to be 0.784 metres squared area, which is something that you multiply these two together and you get that in metres squared. That's what they're talking about. They use that in a calculation. So here they calculate their entrance dose based on these numbers. We don't need to do that because we can our simulator already creates entrance dose values, so we don't need to use their I was going to try and work that out and use their formula, but it's a little bit long-winded and I don't think it's worth it. So, so we don't really need this column. It's just there because the paper reports it. We do know that they used mag 1 in their standard condition, but we don't know what that setting was. Now, I'm going to assume that mag 1 is 3 times the dose of mag 0, because this paper that I've looked at is showing us roughly 3 times the dose for the 11 centimeter mag compared to the 23 centimeter mag. So I haven't got anything else to go on. I've looked at another paper or two. I know that that's about right, but so what I've done is I've given the pulse width, which we don't know. I've come up with a pulse width of 0.028 seconds, or about 30 milliseconds for the standard condition, and I've gone to about 10 milliseconds for the optimized condition without the mag. So the difference here is because of these mag settings, okay? And the values, I don't know what they are. They're reasonable, as we've seen here. This one, for example, is a pulse width of 80 milliseconds. You can go up to 66 milliseconds if you're doing 15 frames per second. So, but that would be continuous fluoro. So I think it would have to be at least half of the time the pulses would be off. So that's why I've gone with 30 as a maximum, or 28 milliseconds as a maximum. Now then, they tell us that the source image distance, so the distance between the X-ray source down here and the detector, was at 120 centimeters maximum when they were using the long gap, the big gap between the patient and the intensifier. And they tell us that it's 90 centimeters when they're bringing the intensifier really close to the patient. They are also telling us that the they're also telling us that skin to source distance is a fixed constant of 60 centimeters. So the distance between the X-ray tube and the table, the back of the table where the patient is a constant 60 centimeters. So by taking that away from the source image distance and estimating the patient thickness to be about 25 centimeters, I've calculated an object image distance. So in the large gap system, then the object image distance would be 35 centimeters, and in the small gap, probably about 5 centimeters. You wouldn't want to get any closer than that. Now, we don't have these numbers. They're not in the paper. They should have put them in the paper, really, because it's one of their variables, but they've not given us those numbers. They've given us numbers that we could use to work these numbers out, but it's a little bit unclear. So I've worked them out. So that I can, confusingly in the paper, they've also given us a source object distance of 43 centimeters, which I can't work out because the source to skin distance is surely the same as the source object distance. So in the paper, they've both told us this distance at 60, and they've also told us this distance is 43. One is wrong, one isn't. I don't know. I don't know. I haven't quite understood perhaps what they mean by source object distance and source to skin distance. I'd have thought those were the same, but anyway, I've chosen to ignore this and just come up with just use these numbers. And then what I've done is I've worked out the distance of the image intensifier from the table. Because I need these numbers for my simulator to simulate for this simulator here to simulate what I need. So basically I've got all of the figures from the paper that they set their independent variables as. So the independent variables, as you know, in an experiment, the independent variables are the ones that the researcher is in control of and change between the two conditions. The constants are either not in control, or they're things that you're going to try and keep the same, even if you could change them. So these are the constants. Now it tells us, obviously the patient thickness is a constant, I've just guessed at 25 centimeters. The fluoroscopy time they tell us is 30 seconds, so I'm going to use that. The tube voltage they tell us is 78 kV, so I'm going to keep that. The tube current, they said that one was 66 mA and the other was 60 mA. Now my settings on my machine won't let me give 66 or 60, so the nearest would be 56 or 70, so I don't want to make such a big difference, so I'm just going to stick it at 63 as a constant basically, although it was slightly variable between these two, but I don't think it would make much difference. And as I've said, they've given us the source object distance, but I don't know what that means because they've also given us the source object distance as a different number over here. Okay, they've given us results in dose area product and entrance surface dose. They've also given us effective dose, which is very clever of them. And to do that, they used this computer program, which had a Monte Carlo data set from the NRPB SR262, and they also used the ICRP tissue weighting factors. So this is it's not complicated, but it's time consuming and you have to deal with a lot more stuff. And as you can see, I've already got 4 screens going here, so I'm going to leave that out. So we haven't got effective dose, but we are going to calculate the dose area product and we are going to calculate the entrance surface dose. They use different units of dose, but I'm going to just use the units that my simulator produces. Now, the maximum tube heat is also a value that I've got here, and it's also a value that's mentioned in the manual as something that heats the X-ray tube up. So although we're talking about optimizing patient radiation dose, it's also nice to be kind to our machinery. So I'm going to also, because I've got the number and it's in degrees centigrade, but in machines they tend to use what's called heat units, which I won't go into the detail of what that means, but it's basically centigrade will work for us. So let's have a go. So let's plug the first numbers into our simulator. Okay, so let's make the simulator a bit larger on the screen. Okay, so the first numbers we want to plug in are let's do the source image distance, which is 120 centimeters. So okay, so 120 centimeters is the source image distance. Now the distance from II to table is, in this case, 60 centimeters, and this is this number here. So we'll have to plug that one into there. It assumes there's no gap between the patient and no thickness of the table and all that, so you have to add all that in to patient thickness on this simulation. So 120 and 60. So we've got those two talked about. Now collimation, it says 28 centimeters by 28 centimeters, and it is already set to 28 by 28, so that's good. So I think that's this screen complete. So so we'll move on to the exposure tab. Now on the exposure tab, it wants a setting of tube voltage of 78, which is there, 78, and a tube current of 63, and it is there, 63, and it wants a pulse width. So pulse width is the exposure time per pulse, yeah? So it wants a pulse width of 0.2028 seconds, which is 28 milliseconds. So we need to increase this to 28 milliseconds. Okay, and it wants a pulse frequency of 15 pulses per second. So we're going to increase this to 15. Okay, what this graph is showing you is the actual dose for the whole exposure, for the whole 30 seconds. So as you can see, the things that we've been doing have been increasing it. So it's gone off the scale there. We'll bring it back in a minute. So we've got that set, we've got that set. Field of view we don't use. MAG1, that's included in this pulse width which we've set. The source image distance set, the detector patient distance is set, all that's set. So everything else is set and we're ignoring that one. So we're all ready to go. So what I'm going to do, oh, it wants 30 seconds of exposure. 30 seconds. So this is set at 30 seconds of exposure, required time 30 seconds. So I'm going to just want to reset this to 0, the heat. So the heat units are going to come up on here. And we just want to, in the data here, I'm just going to have accumulated DAP, not predicted or dose length point. Okay, I'm going to reset the accumulated DAP as well. Okay, so we're going to get our temperature from here, and we're going to get our accumulated DAP from there, and our dose per second is already displaying here. That's what that's set. So I'm going to run this now. Let's hit expose. Off it goes. So it's going to take 30 seconds, obviously, to heat up. So it's climbing. And we're heating the tube up. It's cooling down really quickly, so this is not challenging it. It's not going to get hugely hot here. As soon as it heats, it's sort of cooling at the same rate, so it's just staying constant. It's just climbing slightly, 200 odd. So okay, there we have it. 214 degrees was the maximum. So we can put that. So what we're going to have to do is we're going to have to minimize this down, and we'll have to write the numbers in here. So the maximum heat was 214. In fact, what I'll do is I'm going to put it over to the side here, cover up the paper. (214°C). Okay, so the entrance surface dose rate was 197 times 10 to the 5. Sorry, 1.97 times 10 to the 5. So that's equals 1.97 times 100,000. So that gets us so that gets us that many micrograys per second. And if we convert that into milligray, that equals that divided by 1,000. So 197 milligray, because microgray is a very tiny number per second. So that's not totally SD. If we multiplied that by 30, then we'd get, let's do that. So multiply that by 30, we'd get the total entrance surface dose. So put that in brackets, and then multiplied by, and then 30 seconds. Oh, put 8 there. Multiplied by 30. Okay, so that's our total dose for that one. And then the DAP is 2,333. Okay, so we've got our dependent variables for that condition. Okay, so now what we need to do, let's save that as so that was a total of 793.8 MAS. Let's put that in as an MAS. Total tube charge in MAS, and that was 793.8. Okay, we'll add that extra dependent variable there. So let's now change our factors. So we're going to go to, let's go back to the dosimetry level. So now we're changing our source image distance to 90. So we drop this down to 90. So that's actually, if you look at that, that's actually increasing our radiation dose. If everything else remained the same, it's gone off the scale there. But never fear, because what's also going to change is the distance from the image intensifier to the table. So that's going down to 30, so we're bringing the intensifier right in close to the patient. So only 5 centimeters away from the patient now. So bang, so that's brought it back to the same. So that's fine. Now next we're going to what else do we need to do? So we've done that. Oh, collimation. We're going to collimate to 11 centimeters, aren't we? Yeah, instead of, so it's going to be 11 by 11 instead of 28 by 28. So we need to bring these in to 11 centimeters. So that's not going to change the rate of radiation dose, but it will change the area that the radiation. So we won't know that what that effect is until we've done the exposure and we've calculated the DAP. So that's now 11 by 11. So that's this screen done, I think. So now we can go to the exposure tab. We want to go to 7.5 frames per second now. So we're going to drop this down to 7.5 frames per second. And we're taking the mag off, so we need to go to 0.11, so 11 milliseconds instead of, the pulse width is 11 milliseconds instead of 28. So there's 11 milliseconds. Okay, so that's all of those done. Now we've changed that, patient's the same thickness, we're going to run it for 30 seconds, the KV remains the same, the MA remains the same, we're not ignoring that. So we're ready to go, I think. Now you can already see that the dose burden, the area under this graph is already smaller. So let's reset this and reset this and hit the expose button. So it's going to run for 30 seconds. So it's struggling to heat the tube beyond room temperature at this point. So wait for 30 seconds and then we can put our new dependent variables in. Okay, done. So it got to 57 degrees centigrade. So it wasn't getting the tube hot at all. And the dose area product became 125.71. Let's just say 126, because round it up. The microgray was 2.3 times 10 to the 4, so that's equals 2.351 times 10,000 this time, instead of 100,000. Okay, and the milligray, if I bring that same calculation down, it gives us 705. So significant drops. And MAS, 156 MAS. Okay, now what we can't tell from this experiment is the image quality, how the image quality fared, because obviously the picture was tiny, so where it had been magged up, it was small, and also there's less dose, so it might have been a little bit grainier maybe, I don't know. They do not mention that the image quality was reduced, in fact, and they show some pictures of before and after, I believe. They seem to be able to carry on and do quite a lot of these injections without any complaint. Yeah, so this was one picture and this is another, and you can tell this is a bit smaller, obviously, difficult to see, and grainy as well a little bit, maybe, in my imagination, I don't know. But they were willing to accept this, and that's the point about optimization, isn't it? As long as it's diagnostic, then you should be willing to accept it. So there you go. That's how to do a little experiment to prove the point of the paper and to create your own data using TechnicVR as the simulation. And of course you get you get this visible difference in the dose burden for the patient between those two situations.